Okay, take it away.
Alright, good morning everyone. We're Team Kayakity Quacks, and we're doing a hoist to transfer athletes from a wheelchair to a kayak. My name is Jennifer Batron.
I'm Kyle Mooney.
I'm Javier Mendez.
And I'm Andrea Hernandez.
So a brief overview of what we'll be talking about today. We'll be starting with some background information about the project, the scope of the project, what we're designing for, what we're trying to build. Talking about some of the specific specifications that we're designing towards. And then one of the previous designs we came up with, and then the final design that we came up with this quarter, going into then the individual components that make up that design, and then going deeper into the engineering analysis, talking about the manufacturing, the test plan, and cost. So we're working with Disabled Sports Eastern Sierra, and they're located up in Mammoth Lakes, California, and one of the programs they do every spring and summer is kayaking events. And the big problem they have with these is transferring the athletes from their wheelchairs to the kayaks. What they do right now is they manually pick the person up, the people wheel their wheelchairs up next to the kayaks on the shore, and they pick the people up and manually put them into the kayaks. This isn't ideal though, because it restricts the independence of the athletes, and we want to give them as much independence as possible so that they can do as much as they can. This is part of the least restrictive environment again. And so the big goal of this project is to design a hoist to transfer them safely from their wheelchairs to the kayaks.
So whenever we have to adapt a device, we want to make sure to analyze the underlying components of the skill, the current capabilities of the individual, and match the modification efforts to capabilities, evaluating the modification effectiveness and safety. Because we're developing this device for Disabled Sports Eastern Sierra, they have a wide variety of athletes that range in ability levels, so we need to accommodate for that. To do so, we are implementing the least restrictive environment, as Jen said. This quote is directly off of their page. They want to be able to provide the facilities to as many athletes as possible, so we're going to help make that possible.
So these are some of the main specifications that we came up with for our design. One of the big concerns that Disabled Sports Eastern Sierra had was the storage space. They don't have a lot of storage, so they wanted to keep the small storage footprint so they can, have it handy, and also so they can transport it in the back of a pickup truck or in a van. So we had restrictions on the length and the width, the height, to keep that kind of within a reasonable size. Also the weight, since the people are going to be carrying this device from the truck to the shore, we want it to be something that's not too heavy, so a regular person with regular strength could carry this easily. Also the operator force currently, since the people are manually picking up the people from the wheelchair and putting them into the kayak, that puts a lot of strain on the operator. So a big goal of this device is to limit that strain on the operator and make it a lot easier for them. And finally, just the time. We don't want to take a lot of time for both the assembly of the structure, but also time in between transferring the athletes, each individual athlete, since it's going to have to be one at a time. So this was our original concept design that we came up with last quarter, and it's called the mover, and how it basically works is it's this rectangular frame structure, and the person in the wheelchair would wheel up to the middle of this structure here, and then there's a chain hoist, a pulley attached to, and there's a sling attached to the chain hoist. And so they would attach themselves to the sling, and they could raise themselves up. Someone else would then push this so it's over the kayak, and then they would lower themselves down. Some concerns came up though at the beginning of the quarter though. Primarily, it limits the independence of the person. Since someone else has to push this device, the athlete can't do it all themselves. And so that was something we wanted to address. Also the concern, since this is a fairly small footprint there, there's the concerns of tipping since this is uneven terrain on a lake shore. The possibility of tipping the structure over, we don't want that to happen. And so we came up with a redesign. We worked a lot this quarter on redesigning. And so we looked at different designs that we come up with last quarter, brainstormed some new ideas. And we're really trying to focus again on the independence of the athlete to give them that sense of independence, the sense that they can do it themselves if they're capable. And we wanted to make it feel secure, so with the mover design, they would be suspended while the mover's being pushed over the kayak. And we felt like that could be, maybe not that secure feeling. So we wanted to minimize that, make them feel as secure as possible during the process. And then finally, we wanted to make the device itself non-intrusive. We didn't want to make it obvious that we're making this adaptation. So this is our final design that we came up with. As you can see, it's a basic A-frame design. And so what happens is the kayak would be situated along the side here, and then the person in the wheelchair would wheel up alongside it. Again, there's a trolley up there where there's a chain hoist attached, and there's a sling attached to the chain hoist. And so the person would put themselves in the sling, again, pull themselves up, and then there's a bar in front here where they can hold on to for additional support. And then if they have the strength, they can pull themselves along so that they would be over the kayak then, use the chain hoist to lower themselves into the kayak, and then they'll be ready to launch.
All right, so now that you've seen our final design, we're going to go ahead and walk you through each one of our components. So first and foremost, obviously one of the most critical components is the overhead beam. At first, we're a little stumped, how are we going to get this person with a disability, from point A to point B. And it just so happened that one day we're frolicking down the halls of 192 actually, and we look to our left, and I don't know if you guys have noticed, but there's actually these message boards that hang on what are called box rails. And we're like, hey, why not try something like that for our design? So we further researched it, and it turns out that this type of design is commonly used for boneyard doors. The existing products were primarily made of galvanized steel, so that wasn't too good because of corrosion. But we're like, hey, it might be a good idea. Let's still try to roll with it. Had a decent yield strength of 29 KSI. So we decided to further analyze it. We did this by creating a finite element analysis model. We validated the model, and once the model was validated, what we did was that we put a 500 vertical load on it right in the middle. So what you're seeing right here is actually the cross section of the middle of the beam, where one would expect to see the biggest deflection and the highest stress. Unfortunately, we ended up getting values of, as you can see, max stress was 157.9 KSI, and the yield strength was 29, so that's no good, unfortunately. So we had to scratch that idea. Click next. So then we kept on thinking, right? So we decided to look into I-beams, specifically 6061 T6 aluminum I-beams. Why? Because aluminum doesn't rust. It's pretty lightweight, so it could be a good material to use for our application. As you can see, this is the I-beam that we looked into specifically. The dimensions are 3 inches by 2.5 inches and with a thickness of 0.15. Yield strength a little bit higher, 39 KSI, and the weight is 2.03 pounds per foot, so that's not too bad either. Initially, what we did was simple calculation back to CE 204 days, and we did a maximum deflection. We were able to get a value of 0.14 inches, which is, and that's maximum deflection right in the middle with a load of 500 pounds. So that's not a lot, and that's a good thing, but we're not really interested in how much it can deflect as much as we are of the stresses. So if you click next. We also did a FEA model of that, and to validate it, we used the calculations that the maximum deflection, compared that theoretical value to what we had in our model. We were able to get it down to a percent error of 5.3. So we realized it was fairly good model. And then we decided to, again, apply the 500-pound force vertically down. And in this scenario, we're able to see a max stress of 14 KSI with the I-beam. And again, to remind you guys, the yield strength of that was 39 KSI. So that's a good sign. So on to the next component, the trolley. This component, we decided to go ahead and just already buy it pre-assembled. The reason for that, it was that it would have all the bearing calculations already made so that it can smoothly travel through the I-beam without much effort. Again, this is going to be manual push, and as Jennifer mentioned before, we will add a little handle to it in case the user can't move laterally by himself. A helper can grab from the handle and push him along. Thank you. So on to the next component, which unfortunately you couldn't see in our SolidWorks model, was the chain hoist. Again, this we were going to go ahead and buy it pre-assembled. The one we're looking at specifically is rated to half a ton, which is about 1,100 pounds. And it's the reason we chose the chain hoist was because of its great mechanical advantage. So in this particular item, in order to lift the half ton, you only need 49 pounds. And so in reality, they're going to be lifting their own weight, which shouldn't be more than 500 pounds. So we should see about, they should need about half of 49 or about 25 or so. So another thing that's very good about this product is that the vendor is able to have a custom chain length. So that way, we don't have like chains dangling all the way to the floor, hitting people in the face, nothing like that. We can just have it custom made so that the user will be able to use it good. Another component of our design is the sling. Right here we have a prototype that we made, and I don't know if you guys remember, myself and Dr. Taylor, you guys weren't here last time, but we actually demonstrated with Jennifer by lifting her. We won't do that today, unfortunately. But again, some advantages of the U-sling is that it's very, very easy to transfer in and out of. A lot of other sling designs, what happens is that you have to lift the user up so it goes underneath their butt. However, this U-sling, it simply slides down their back, and as you can see, this it wraps underneath the legs and up. And from here, here's where you would connect to what's called a gambro, and which kind of looks like a hanger, and that's connected to the chain hoist, which then pulls you up. So now, how are we going to connect the top beam to the legs? Right? So we're going to go ahead and make this connection. We're going to manufacture it ourselves. The attachments that we have are going to come with the telescoping legs, which Kyle will go into further detail. And specifically, how we're going to attach this to the I-beam, we're going to connect them most likely with universal head aluminum solid rivets. There's going to be 4 of those on the top, 2 of those and underneath. And that's just to provide a good, solid connection.
So here we have the legs. We know there's going to be a lot of stresses in these legs. So we chose to do an A-frame. And the bar in the middle will prevent from blowout. But we wanted to do telescoping tubes for storage reasons. And then we decided that also the telescoping tubes would allow us to make it adjustable in the height. So if you're on uneven terrain, it could be a straight bar across no matter what. We've also been told by our advisor, Sarah, to not manufacture these ourselves because it's very difficult. There's a lot of wiggle. So we will purchase these. Each of these will be in 2 4-foot sections, and that is that's each telescoping side will be 2 4-foot sections. And that'll give us a total height of about 6 feet in the air, so it could easily be reached to the trolley. And then also at the bottom, we're going to have little feet with rubber soles so that we could, so that it could be on like gravel or something if it needs to be. So we know there's going to be very, very high stresses, so we exaggerated the load amount for each of these. The main problem was buckling, or buckling was one of the main problems, and we chose to do a pin-to-pin ratio, therefore giving us a higher diameter that would be needed with the amount of stress. And so with that, we came up with 2.2 inches for the diameter of a thickness of 1,000 or 1/10 of an inch. And then for the moment, that moment is caused by the person sitting in the very center. So against one beam, it was 18,000 inch-pounds, and the width for that would have to be 2.8 inches. So here's our manufacturing plan. Basically, we're trying to buy and gather all the materials before the end of the quarter, and then we'll move on from there. Each component is pretty much on its own, and we could manufacture them separately, except for the attachments or the leg connections. We want the overhead and also the legs before we build those together. And we hopefully have all of those parts by the end of the quarter, and then have it built by week 5, and therefore give us time to troubleshoot and optimize more. So here's our testing plan. There's a few, like the weight and the length we could just measure, that's easy. For subjective ones, we're going to ask people who are involved in the project or involved with the kayaking program to really tell us and give their approval. We also have the weight capacity, which we'll just do with 500 or 250 pounds maximum, and for the time to assemble and time to operate, we'll teach people how to use it, and then let them do it and time them to do it, not us. So here's a cost analysis of everything. We went very conservative, but still we're borderline. There are a few things to notice that the sling, a retail value of the sling is $182, but we just built one for about $10, and obviously that's not going to be the exact one, but if we wanted to, we're sure we could do it a lot cheaper. And we also have very high estimates on the things that we are manufacturing, but still it comes out to a total of $1,416. So we are going to double and triple check our numbers, because we will not have mistakes, or we cannot have mistakes at all.
Alright, so finally wrapping up, since we did do the redesign this quarter, there's still a lot of optimization and further design that we can do. So additional features, one of the things with this design is, since the person is wheeling up to this device, they can't be right at the water's edge. And so launching the kayak, we have to figure out how to do that so that they can hopefully do that as independently as possible. So one of the things we want to do, if we have the time and resources, is create some sort of system so that they have rails on the side maybe, so they can push themselves off once they get in the kayak, so they can actually launch and dock again independently. In addition, for the redesign, addressing some of the potential problem areas of this design. So looking at weight, for instance, a lot of these components, they're not too bad by themselves, but overall it definitely adds up for the overall weight of the structure. Also the cost, as you saw in the previous slide, we're very borderline up to our $1,500 budget. And so just making sure, looking at all of our costs, seeing what we can reduce, seeing maybe if there's parts that we can do ourselves that would be cheaper. And then also the length, just keeping this again in that small storage footprint. We looked at potentially our top beam member is currently just a single member, and so in order to accommodate both the kayak and the wheelchair, it has to be about 6 feet long. And so that could potentially create a problem if you're trying to fit it in the back of a van or a car. So potentially looking at other options if there's a hinge member, if that needs to be. So after we finish our optimization, we need to order our parts. A lot of those we've already kind of spec'd out, figured out what we kind of want, and then start the manufacturing and building. Are there any questions?
I have a question. For that bar that goes across that they grab to, how far away is that? I'm just thinking, what if they can't reach it?
We're not going to build that yet until we have them sitting there and we find the optimal spot to put it.
Yeah, okay. Another problem is also figuring out the right height so that once they're sitting in their wheelchair, they can grab it comfortably. Once they raise themselves up, they can still grab it comfortably. So we haven't
go under it.
Yeah, and then also, I don't know if you can see, but we're going to have attachments on the side, so that way the bar can be lifted up once they're in the kayak, if it's still too short for them to pass under when they're launching.
Are you worried about this thing wishboning though, if you don't have something connecting the one A-frame to the other?
Well, the top member is really the structural support.
Like bending it out like this.
Yeah.
The two A's going.
And
that
the-
I mean,
one
you're gonna
is-
have aluminum tube that's not going to be, that's gonna have some flexibility. So that's why, you know, we've talked about figuring out how to, you gotta come from both directions and.
Could they strengthen it with ropes on the bottom? Because, you know, two of the feet are going in the water, you could throw a strap across between the two to stop
Oh,
them
to
from
keep it from going
sliding.
up.